we talked about Euclidean distance and how Euclidean distance is related to the cosine of the vectors. And Euclidean distance is a good measure to measure distance, but you could actually generalize it. So there's a family of p-norm distances which look like Euclidean distances, except instead of the square here, you have a parameter p. Right. And that parameter p can actually be pretty useful in a number of applications. So if you set p to 2, you just get your normal, comfortable Euclidean distance that you are familiar with. If you set p to 1, you get Manhattan distance, right? Everybody remember what Manhattan distance is? So when I'm computing the distance between the point in the lower left and point in the upper right, Euclidean distance is just the length of the straight line. Manhattan distance is, imagine you are walking down city blocks. So basically you can't walk straight from one point to another. What you have to do is you have to walk in this funny little zigzags. And all the distances, the red and the blue and the yellow, are exactly the same. It's basically you take the difference in the x value between the 2 points and add the difference in the y value between the 2 points. So that's Manhattan distance, and you get that by setting p equals 1 in the p-norm. Now, what's neat about the p-norm? Question? Oh, lost the mic. Thanks. The nice thing about the p-norm is you can use other values, and it turns out that when you stick other values into p-norm, you get some pretty interesting distance functions. So if I set p to be a really, really big number, right, so this number becomes really, really big. Think about what starts to happen, right? I have distances between the w coordinate of q and the w coordinate of d, right? Vectors q and vector d, they're going to have a bunch of these little distances along each coordinate. And now what I'm doing is I'm raising the difference into a really, really big power. Right? So all the numbers are going to get big, but the biggest difference is going to grow disproportionately large compared to everything else. Right? Is that obvious why that's happening? So imagine you have a parabola, right? So let's say the individual distances, qw minus dw, are in the range between 0 to 1, just for no good reason, right? So the distances would be here, 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 right? If I raise the distance to the power of 1, that's what I get, right? So the relationship is linear. If I raise it to the power of 2, I get that. They're all made smaller, but the difference between the biggest one and the next biggest one has increased dramatically, right? So there was a relatively small difference here and here, but there's a much larger difference here. If instead of raising it to a power of 2, I raise it to a really big power, this curve is going to look like that. So the difference between the max and the second max is going to become very, very pronounced. So an interesting thing that happens with the p-norm is if you set a p to a big value, it starts behaving like a max over the individual dimensions of the small difference. And a max, if you remember your logic, it behaves kind of like a logical OR in the formula. If you set p to 0, or near 0, you get the opposite behavior. So you basically get a behavior that looks like the min, and that is similar to how a logical AND behaves. And as you set p to different values between 0 and infinity, you will get distance functions that have unusual behaviors that are not the same as the Euclidean distance. So let me give you an example. So what I have here is I have a bunch of vectors or points in two-dimensional space. Let's say I'm measuring the distance from A to all other things. Right. If I'm using Euclidean distance, normal Euclidean distance with p equal to 2, then points B and C are the same distance from A. Is that clear why? Right, they're on the same ISO line. So B and C are equally far, and D is a lot further than either of them. If I start using a P norm, say with P of 0.7, I get a very different picture. With P of 0.7, point C and point D are equally far away from A. And B is a lot closer than either C or D. So what you're doing is you're changing the notion of, you're basically warping the space. You're changing the notion of distance. And why is that? Why is that useful? Well, it's useful if you're considering simultaneous differences across multiple features or multiple dimensions, multiple words of your space. So both B and D, they're different from A only along dimension 2. They're identical along dimension 1. The point C has differences both in dimensions 1 and dimensions 2. Now, Euclidean distance doesn't make a big difference. It doesn't see a difference between B and C. So as far as Euclidean distance is concerned, whether you have a significant deviation on one word or on 2 words, it's about the same thing. Right? That's B and C. P 0.7 makes it really, really dramatically different. It says that if you have deviation on 2 words simultaneously, that's a lot different than having just a single word difference and the other word being identical. So by playing around with P, you can get very different distance functions that can sometimes be useful in some applications. Okay. So there's a few more distance functions. I'm not actually going to talk about them. These are appropriate when you treat document queries as histograms. There's a whole lot more of them on that bit.ly link, which points to an IBM site. And I guess, as always, remember that when you're doing this, you still need to set the weights. You can't use frequencies. Doesn't work for text. And and these are distances. And in the rest of the course, we're going to be talking about similarities. So if you decide to use distances anywhere, make sure you convert them back to similarities. Just take 1 over the distance or 1 minus the distance or negative distance, whatever you think works best.